Let us now talk about another section in this chapter, surface chemistry. We have now colloids to discuss. See, we have already talked about catalysis, we have already discussed about adsorption. We are now going to talk about colloids. Let us find out what are colloids. See, if you mix two substances, these two substances, mixture of these two substances may be a true solution, it may be a colloidal solution or a suspension. This classification is based on particle size. If the particle size is less than 1 millimicron, then the substance is described as true solution. It is described as true solution. When the particle size is less than 1 millimicron, you call it true solution. If it is in the range of 1 millimicron to 1 micron, then you call it colloidal solution. If it is greater than 1 micron, then it is described as suspension. Mixture of two substances in which the particle size is less than 1 millimicron is described as true solution, while true solution is homogeneous, whereas the other two are heterogeneous. If the particle size is in the range of 1 millimicron to 1 micron, then you call it colloidal solution, and if it is greater than 1 micron, you call it suspension. So, mixture of two substances can be classified into three types: true solution, colloidal solution and suspension. Classification is based on particle size. While true solution is homogeneous, the colloidal solution and suspension are heterogeneous in nature. Now, our discussion will be about this colloidal solution. The particle size. Particles are not generally molecules, they are clusters of molecules, or it may be a polymer, macromolecule. Let's learn about colloidal solutions in detail. Colloidal solution is made up of two components. Colloidal solution is made up of two components. One is called as disperse phase, and the other one is called as dispersion medium. The two components present in colloidal solution are called as disperse phase and dispersion medium. As in case of true solutions, you call them solvent and solute. Here you call them as dispersion medium and disperse phase. This corresponds to solvent and this corresponds to solute. Or I can put it in this way: the continuous medium is dispersion medium, and the particles which are present discontinuously they constitute disperse phase. So, these are the two components present in a colloidal solution. Let us now learn about classification of colloids. Classification of colloids. See, I would like to repeat this. We said when we mix two components, three possibilities arise. One of them is colloidal solution, where the particle size is 1 millimicron to 1 micron, anything in this range. And another thing we said is colloidal solutions are heterogeneous, not homogeneous. And one more thing we have said is that the two components are named as disperse phase and dispersion medium. Now, we are going to talk about classification of colloids. Now, number one, classification based on physical states of disperse phase and dispersion medium. Classification based on physical states of disperse phase and dispersion medium. See, disperse phase may be a solid, liquid or gas. Dispersion medium also may be a solid, liquid or gas. Based on this, you can think of how many possibilities? You can think of 9 possibilities. See, solid in solid, liquid in solid, gas in solid, then you have solid in liquid, gas in liquid, liquid in liquid. So, in this way you can have 9 possibilities. Out of 9 possibilities, one possibility is ruled out, that is gas in gas. Gas in gas is always a homogeneous mixture. Always it is the interaction is at molecular level, which is less than 1 millimicron in size. So, gas in gas is always homogeneous, so it is not a colloidal solution. So, how many types of colloidal solutions based on physical state? You have 8 types. 8 types. Based on physical states of disperse phase and dispersion medium, you can have 8 different types of colloidal solutions. I am going to give the list of 8 types of colloidal solutions with examples. This is very, very important part. Generally, questions are asked from this part. So, I am going to give a tabular form of 8 different types of colloidal solutions. Look at the different types of colloidal solutions classified on the basis of physical states of disperse phase and dispersion medium. You have solid in solid. I mean, disperse phase is solid, even dispersion medium is also a solid. Such a colloidal solution is represented as solid sol, and examples are gems. Gems are semi-precious stones, for example, rubies, emeralds, sapphires. These are examples of gems. Please remember, alloys are not solid colloidal solution. Alloys are always homogeneous, they are true solutions. Look at this case, liquid in solid. Here you have disperse phase as a liquid and dispersion medium is a solid, and it is described as gel. Examples are cheese, butter, even shoe polish. So, liquid in solid colloidal solution is described as gel. Examples are cheese, butter, shoe polish, etc. Then you have gas in solid. Dispersion medium is a solid and disperse phase is a gas. It is called as solid sol. Examples are pumic stone, foam rubber. Foam rubber consists of air gaps in between the continuous solid phase, that is rubber. Then you have solid in liquid. You have solid particles present in a liquid dispersion medium. Such a colloidal solution is simply called as sol. Examples are paints, cell fluids. Cell fluids contain macromolecules like protein molecules, DNA molecules in a liquid dispersion medium. Then you have liquid in liquid. This is a colloidal solution where both disperse phase and dispersion medium are liquids. Such a colloidal solution is called as emulsion. Milk is an emulsion. Cold creams are also taken as examples. Even grease, vanishing cream is also an emulsion. So, it is a case of liquid in liquid colloidal solution. Remember, this type of colloidal solution can be obtained by mixing two immiscible liquids. Two immiscible liquids on mixing give emulsion if you shake it thoroughly. Then you have gas in liquid colloidal solution where you have particles of gas bubbles, small bubbles, tiny bubbles of gas present in a continuous liquid dispersion medium. Such a colloidal solution is called as foam. Froth, soap lather is an example of such a colloidal solution. Then you have solid in gas, which is called as aerosol. Solid particles present in the continuous gas phase. Example is smoke. Smoke consists of carbon particles present in gas dispersion medium. And you have lastly liquid in gas. Here you have droplets of liquid present in the gas dispersion medium called as aerosol. Fog, cloud, mist, these are examples of aerosols, that is liquid in gas dispersion medium. One case is missing, that is gas in gas. As I told you in the very beginning, gas in gas is a case of true solution. It is a homogeneous mixture, it is a true solution, it cannot be regarded as a colloidal solution. One important point I would like to emphasize here is sometimes we get a doubt whether to treat a particular colloidal solution as a solid in liquid case or liquid in solid case. It is very easy to decide. The physical state of colloidal solution is the physical state of dispersion medium. If the colloidal solution of liquid and solid is a solid, then treat solid as a dispersion medium. If a colloidal solution of liquid and solid is a liquid, then treat liquid as a dispersion medium. So, physical state of colloidal solution is the physical state of dispersion medium. That is about this classification. We will be moving on to another type of classification after this. Now, we were talking about classification of colloids. Classification of colloids. Another classification we are going to discuss is based on interaction. This classification is based on interaction between disperse phase and dispersion medium. Disperse phase and dispersion medium. The classification is based on interaction between disperse phase and dispersion medium. Here, colloidal solutions are classified into two types: lyophilic and lyophobic. Here, phily means affinity and phobia means fear. Lyo pertains to dispersion medium. So if there is a great affinity between disperse phase and dispersion medium, then such a colloidal solution is called as lyophilic. If the affinity between disperse phase and dispersion medium is very less, then you describe it as lyophobic. Let's discuss some points of differences between lyophilic and lyophobic colloidal solutions. Lyophilic, lyophobic. Great affinity exists between disperse phase and dispersion medium. Very low affinity exists between disperse phase and dispersion medium. Disperse phase and dispersion medium attract each other reasonably well. In this case, the attraction is very less. Lyophilic salts are reversible, whereas lyophobic salts are irreversible. That means if the sol separates into disperse phase and dispersion medium, again shake it, it will regenerate, whereas this cannot be regenerated by shaking. Lyophilic salts are prepared directly. If you mix disperse phase and dispersion medium and just shake it, generally lyophilic salt will be prepared in this way. Whereas here special methods are used. Special methods are used for preparation. They cannot be prepared directly. Lyophobic salts cannot be prepared directly. These are formed by organic substances and inorganic substances form lyophobic salts with water as a dispersion medium. Particles are neutral. Generally particles are neutral in case of lyophilic salts, whereas here the particles they carry charge. They may carry positive charge or negative charge. One more important point of difference I'll mention here, that is regarding coagulation. Salt destruction of colloidal solution is called as coagulation. These are coagulated very easily by adding small amount of electrolyte. These are not coagulated easily. These are stable, these are not that very stable and easily coagulate upon addition of small amount of electrolyte. Coagulate easily, do not coagulate easily. They coagulate upon adding small amount of electrolyte. I told you about another point of difference between philic and phobic salts, that is do not coagulate. Lyophilic salts do not coagulate easily, whereas lyophobic salts coagulate easily upon adding small amount of electrolyte. If you add a small amount of electrolyte to a lyophobic salt, it gets coagulated. Now coming to examples, protein sol, starch sol, gum sol. These are examples of lyophilic colloidal solutions. Metal salts, here the particles are metals. Metal hydroxide sol, metal sulfide sol. These are examples of lyophobic salts. So arsenic sulfide sol is an example of Lyophobic. Ferric hydroxide sol is an example of lyophobic sol. So, in this way, metal sulfides, metal hydroxides, any I can say any insoluble salt of a metal can form a lyophobic colloidal solution. Now, regarding classification, another type of classification of colloidal solution is based on nature of particles. Nature of particles. Here we have three types of colloidal solutions: macromolecular colloids, then you have multimolecular colloids, and the third one is associated colloids. So, let us talk about these types of colloidal solutions one by one. There is another classification. This classification is based on nature of particles present in the colloidal solution. Let us take up number 1, macromolecular. As the name itself indicates, macromolecular colloidal solutions consist of large molecules, polymeric species. Large molecules, giant molecules, their size is greater than 1 millimicron, they form macromolecular colloids. These are formed by giant molecules. Example, protein sol. Protein sol is an example of macromolecular colloid because protein is a macromolecule. It is formed by association of large number of amino acid units. Then you have starch sol. You know, starch is also a polysaccharide. It is formed by joining of large number of glucose units. So, starch is a large molecule. Such a molecule can form a macromolecular colloid. So, these are examples of macromolecular colloids. Here the molecular size is large because of their polymeric nature, and the size of the molecule itself will be greater than 1 millimicron, and they form macromolecular colloids. We will move on to the next example, multimolecular colloids. Example for this is gold sol, sulfur sol. Gold sol and sulfur sol are examples of multimolecular colloids. These are formed by aggregation of large number of smaller molecules. If smaller molecules aggregate due to their hydrophobic nature, if they aggregate and form clusters of colloidal dimension, then such a colloidal solution is called as multimolecular colloid. If sulfur is precipitated in water, because sulfur is insoluble in water, large number of sulfur molecules, they tend to form clusters, and these clusters will have colloidal dimension. So, sulfur sol, gold sol are examples of multimolecular colloids. The size of the particle increases due to aggregation of large number of smaller molecules. They do not join, unlike macromolecular colloids, they do not form bonds. Actually, they just form clusters where they have physical interaction, not chemical bond formation. Now, the third type is associated colloids. Associated colloids. These are formed by a special type of molecules. You know, look at this type of molecule. It's a very long chain of carbon atoms taken n times. You have this type of species. Now, this type of species has both, it has dual nature. It has both hydrophilic as well as hydrophobic nature. While this part of the molecule is hydrophilic, it tends to stay in water, whereas this part of it is hydrophobic. This hydrocarbon tail, this is hydrocarbon tail which is hydrophobic, and the carboxylate part of it is hydrophilic because of its polarity, you know. So this type of molecule has two complementary ends, hydrophilic end and hydrophobic end. The hydrophilic end tends to stay in water, whereas the hydrophobic end wants to get out of water. Another case, this is this type of molecules, they behave as soap, and you have detergents also. Detergents will be of this type. Even detergents are having this type of complementary nature in the same molecule. You have a number of carbon atoms. Let us assume that it is a very long chain. Then this hydrocarbon part is hydrophobic, and this sulfonate part becomes hydrophilic part of the molecule. This is a case of, this is detergent. While this is detergent, this is a soap. So soaps and detergents, they give rise to associated colloids. I'll show you how they get associated. But remember, in their dilute solution at a low temperature, in dilute condition, low concentration and low temperature, at low concentration and low temperature, they behave as normal solutions, that is homogeneous solutions or true solutions, or they behave as electrolytes. But if you increase their concentration at a temperature which is characteristic of the substance, below that temperature, they exist as colloidal solutions. I am going to show you how they get associated. Please remember, the molecule has got two distinct ends. One end of the molecule is hydrophobic, the other end is hydrophilic. Let's see how they associate. So this is the depiction of a soap or detergent molecule. It has this, I call it as head of the molecule. It is hydrophilic, isn't it? The charge on it makes it hydrophilic. This part is tail part, and the tail part is hydrophobic, wants to stay out of water. Now when you have several such particles existing in water, then they tend to form a spherical ball-like structure in which their tails are pegged inside and their heads are present outside. The charged heads are present outside and their tails are pegged inside, and they form a spherical ball-like structure which may have 100 or more than 100 particles associated. Because of association of such a large number of particles, the size of the particle will be in the range of 1 millimicron to 1 micron, that is colloidal dimension. This particle is called as micelles. So this consists of 100 or more than 100 particles associated in this way. Their tails are all pegged inside and their heads are outside. So when it is present in water, only the heads come in contact with water. The tails are, because the tails are inside, you imagine it as a spherical particle, all the tails are inside, so tails will never come in contact with water. So they're hydrophobic, tails are hydrophobic, they stay within water. Also the tails are not in contact with water, only the heads are in contact. So these particles are called as micelles. What type of molecules form micelles? Those which have two distinct ends, hydrophilic and hydrophobic. Micelles are spherical ball-like structures which contain about 100 or more than 100 molecules associated, and the dimension is falls within the range 1 millimicron to 1 micron. Such colloids are called as associated colloids. Remember, soaps and detergents form associated colloids, and the colloidal particles are described as micelles. Micelles in the periphery, they have charged particles, charged heads which come in contact with water. Here I would like to introduce two important terms. One is CMC, critical micellization concentration. Critical micellization concentration. I told you at low temperature they exist as discrete particles in the solution and they form true solution. But after a particular concentration, I can say beyond a particular concentration, they aggregate to form micelles. So, this concentration below which the soaps and detergent solutions are true solutions is called as critical micellization concentration. So, the minimum concentration at which these particles aggregate to form micelles is called as CMC, critical micellization concentration. Here, remember, if the tail is very long, then the hydrophobicity of the particle will be more. So, such a particle will be more desperate to form micelles. So, as the tail length increases, as the chain length increases, the CMC decreases, because as the chain length is increasing, hydrophobicity of the particle is increasing, the particle becomes more and more desperate to form micelles. So, it can form micelles even at low concentration. So, CMC, as carbon chain length increases, CMC decreases. CMC stands for critical micellization concentration. So, if I give you examples, look at this example. Imagine I have C17H35CONa, then I have another one C16H33CONa, and then you have C15H31CONa. If different types of soaps are there, then the one which has lowest CMC, the one with lowest CMC will be the one with highest number of carbons. This will have lowest CMC value. Another term I wanted to make you familiar is Kraft temperature. Kraft temperature, this is denoted by Tk. Above Tk, micellization takes place. The temperature below which micellization cannot take place is called as Kraft temperature. Kraft temperature is the minimum, it is the minimum temperature at which micellization can take place. Below Kraft temperature, micellization does not take place. So, the temperature, this is characteristic for different types of soaps and detergents. The temperature below which micellization cannot take place is called as Kraft temperature.